Welcome back, everybody. So we are continuing through 5.2 here, the natural logarithm and integration. So last time we worked through some basic integration examples, so we're going to go ahead and finish up the notes here. So we've got some additional integrals here that are going to be pretty central to anything involving trigonometry. So we've taken derivatives of all of these functions. Now we're going to be taking integrals of all of these functions. The first two you know, sine and cosine. So we've worked with those since chapter 4. But now we're going to add in the remaining trig functions, so tangent and cotangent and secant and cosecant, and how we can integrate them using the natural log function. So let's go ahead and derive one of these. So let's say we wanted to do tangent. So what we're going to want to do in this case is use the fact that we know that tangent is sine over cosine. So our integral for tan x dx is equal to the integral of sine x over cosine x times dx. And now we can do a u sub, so we'll let u equal cosine x. So du is going to equal negative sine x dx. So we're going to have this negative sign, so we'll just note that we'll be substituting sine x dx with negative du. So we're going to get negative integral du over u, which gives us negative natural log of the absolute value of u plus c. But u again is just cosine. Now, the other thing we can do, though, is we can use the fact that we know properties of logarithms and that we've got this coefficient of -1 in the front. So we can also rewrite this, if we wanted to, as the natural log of the absolute value of cosine x to the -1 plus c, which is just 1 over cosine x. So an equivalent expression for the integral of tangent is the natural log of secant x plus c. Okay, so maybe we'll make a note of that here as well. So natural log secant x, plus c. And then similarly for our natural log of sine x plus c, we could add a negative, but given that it's positive, we'll typically just use natural log of sine. And the proof of cotangent would be exactly the same. Now for secant is going to be a little bit different. And so there's going to be a homework example that you work on where you derive secant, but it's a very particular style of proof that you're going to do for secant. So I'll let you think about that one, and then if you have questions, you can definitely come by and ask. All right, so using these then, we'll just use these directly. We can integrate now, again, using composite functions, so we can apply the chain rule to these as well. So for the first example here, we've got cosecant theta over 2d theta, so we've got a half angle expression in here. So we could do, u, choose a smaller font here, u is equal to theta over 2, so du equals half d theta, so then 2 du is equal to d theta. So we can substitute this as 2 times the integral of cosecant u du, which is going to be 2, and now the integral of cosecant is going to be the natural log of cosecant plus cotangent. Plus c. So we could write that as -2 natural log of cosecant theta over 2 plus cotangent theta over 2 plus c. So really, among these, the ones that you're going to probably want to just have memorized are secant and cosecant, because these ones are kind of the longer ones overall. But tangent and cotangent are pretty easy to derive. And then similarly for 2, we've got secant 2t. So we could let u equal 2t. du is going to be 2 dt, which means half du is equal to dt. Secant 2t is actually not too bad to do without a u sub as well, so you could skip the u sub if you wanted to. But if you want to add the u sub in, just keep in mind you do have to change your limits of integration as usual. So if u is 2t, when x is 0, u is going to be 2 times 0. And when x is pi over 6, u is going to be 2 times pi over 6, which is pi over 3. So just keep that in mind. I'll use the u sub, but again, this one is one you could work backwards from. So then we're going to get the antiderivative as the integral as 1/2 integral from 0 to pi over 3 now of secant u du. And so we'll get 1/2 natural log of secant u plus tangent u plus c. And so we'll get 1/2 natural log. So secant of, not plus c. Sorry, this is a definite integral. And we can see here that we could drop the absolute value because secant and tangent will both be positive on the interval 0 to pi over 3. So we don't actually need the absolute value. And so we'll get evaluated at pi over 3 is going to be secant of pi over 3, which is the reciprocal of 1/2, since cosine of pi over 3 is 1/2. So we'll get 2 plus, and then tangent of pi over 3 is going to be radical 3 minus the natural log. And then at 0, we're going to get 1 plus 0. So secant of 0 is 1. Because cosine of 0 is 1, and then tangent of 0 is 0. So we're just going to get natural log of 1 for the second term, so that's just going to cancel. So we're actually just going to end up with 1/2 natural log of 2 plus rad 3. Or if we wanted to, we could write it as the natural log of the square root of 2 plus rad 3. If we wanted to get rid of the coefficient. But either way, perfectly fine as an answer. So secant and cosecant are going to be two that you really want to keep track of and be careful with. Okay. Also in 5.2, we're going to look at direction fields, differential equations, similar to what we started with in chapter 4, but now we're actually going to use it quite a bit since most of our applications involving in particular population size are going to be exponential. So we can go ahead and take a look at this example here. So we have a population of people is changing at a rate given by dp over dt is equal to 1,000 divided by 2 plus 1.2t, where t is measured in years. So if the initial population of people is 1,500, we want to find an equation that represents our population at time t, and then find the population after 4 years. So we know the initial population is 1,500, so that's going to be important to us. So we know that p of 0 is equal to 1,500, but we don't know what p is yet because we only know p prime. So we're going to need to rewrite this expression so that we can then integrate and determine what p is equal to. So similar to what we did with those initial examples last chapter, we can take our differential equation and we're just going to multiply both sides by that dt term, the differential of time. And now, since we've got the two separate differentials on either side, we can actually integrate both sides and figure out what p is going to be equal to. So on the left-hand side, the integral of 1 times dp is just going to be p. And on the right-hand side, we'll have to do a little bit of simplification. We could note that we could just rewrite this as the integral at 1,000 times the integral of dt over 2 plus 1.2t. So you can do a u substitution for this. So you let u equal 2 plus 1.2t. So no, you could do a u substitution if you need to. I'm actually going to do this kind of working backwards without having to worry about that, but we can note that du in this case would be 1.2 dt. So we're going to have to divide by 1.2 in our expression to undo our chain rule. All right, so what we're going to end up with then is 1,000 over 1.2 times the natural log of 2 plus 1.2t plus c. And note, you can always check this answer. If we take the derivative of this, we'll get a 1.2, which will cancel with that 1.2. But again, if you want to do the u substitution, go ahead and do the u substitution as well. All right, so we've got our population function here, but we do need to figure out what our c value is. So we need to figure out the particular population function, and here's where we're going to use the fact that we know that p of 0 is 1,500. So that means that 1,500 is going to equal 1,000 divided by 1.2 times the natural log of 2. Oops. Since 1.2 times 0 is just going to be 0, plus c. So then we get that c is going to equal the difference of 1,500 minus 1,000 over 1.2 times the natural log of 2. So that's going to be some approximation. So if we pull out our calculators, we can approximate that. So what we're going to end up with is 922.3773,495. All right, so we've got this very particular value that we end up with. And then our goal is now to find the population after 4 years. So we'll just note that P of t is going to equal 922.3773 with all those digits, and then plus 1,000 over 1.2 natural log of 2. Natural log of 2 plus 1.2t. So again, kind of a messy function overall. So then at 4, if we plug in a 4 to this function, let's see what we end up with. So we'll have 1,000 divided by 1.2 times the natural log of 2 plus 1.2 times 4 plus 922.3773. So we're going to get approximately 2,519.812. So we could say approximately 2,520 people if we're rounding up to the nearest value, or 2,519 would also be fine. So in this case, I'll just round up. So our population will go from the initial value of 1,500 to a little bit more than 1,020 more people in 4 years. But the key idea here is that we're taking our differential equation to start, and we're integrating it to solve, and that integration is going to result in a natural log function. And what we'll look at moving forward is we'll also get population functions where when we integrate, we end up with an exponential function. All right. So then on the next page, we've got some additional exercises and then one new kind of idea here, which is a slope field or a direction field. So a slope or direction field is a graph of a family of solutions to a differential equation. And so if we look on the right here, all of these blue tick marks represent an individual slope. So in other words, if I were to look at this single tick mark here, this is going to be the slope of our curve at the coordinate, if this is 1, 2, and 3, at 3, 3. So at 3, 3, our slope is this slightly positive slope value. And so we're going to use this slope field to estimate the graph of a function. So if I look at this graph on the right, I'm given an initial value. So this point here on the bottom in black is going to be a nice initial value that we're going to work with. And from that, we're going to approximate what the actual curve looks like. So if I look to the right, I can see that my slope is just slightly positive. So we're just going to try and mimic that slope somewhat, moving from left to right. And then if I go in the opposite direction, I can see that it's actually negative. And there's actually going to be an asymptote here. And note we've been given the differential equation over here. So all these blue tick marks on the right are derived from this natural log of x divided by x equation. All right, so that red curve is a particular curve that satisfies the solution, but remember that there's an infinite number of these, right? So we could draw an infinite number of them vertically shifted up or vertically shifted down. So this red curve that satisfies this particular value at 1, -2 is called the particular solution. And it's particular because we know enough information. So if we just look at the slope field, the whole of the slope field is what we call the general solution. So if we have enough information to find our exact curve, we call it a particular solution. If we're just solving a differential equation and we keep the plus c in, we call it the general solution. So that's going to be plus c, and this one's going to be, for that particular point, 1, -2. So whatever the particular c value is. So it says, find the particular solution to our differential equation and graph the solution that passes through the point. So we've already graphed our solution, but let's look at what our algebraic solution would look like to our differential equation here. So we would separate variables so that the x's are with dx on the right-hand side, and then we can integrate. So on the left, we'll have y. ln of x over x, note we've worked out earlier something similar, but this would be a quick u sub example. So u would be ln of x, du would be 1 over x dx. And then we can substitute in there. So this is going to be the integral of u du, which means that y is equal to u squared over 2 plus c, just as a quadratic. But u, again, is a natural log function. So that means that y is equal to the natural log of x quantity squared. Note, we're not taking the square of x, but we're taking the square of the logarithm function itself. So we can't use any power property or anything like that because this is just a product of two logarithm expressions. And then plus c. And then given our point 1, -2, we can then substitute those values in. So I can substitute for y, substitute for x. And we'll quickly see that -2 is equal to, well, the natural log of 1 is just 0. So this is just going to be 0, which means we get c is -2. So then we end up with our particular solution is going to be y equals the square of natural log of x divided by 2 minus 2. So now this is our particular solution. Whereas this plus c curve that we started with was our general solution. So our particular solutions once we've actually solved for that c value. Okay. All right, so that kind of does it for most of the new material. We'll look below here to some additional exercises. So it looks like there are 3, and they're going to employ things that we did in chapter 4. So both of these questions are going to be fundamental theorem of calculus part 2 questions, where we take the derivative of an integral function. And then the average value is something we also looked at in the fundamental theorem notes. So let's go ahead and calculate both of these quickly. So on the left, excuse me, we can see that we've got f of x is the integral from 3 to 4x minus 2 of 1 over t dt. So this one we could integrate if we wanted to, but again, that fundamental theorem gives us a nice shorthand for evaluating this. So just to recall that, if we have f of x equals the integral of a number, so let's actually just write a number in, let's say 2, or in this case 3, to some function u of x of f of t dt. So note capital F is the antiderivative, of course. Then the derivative, f prime of x, is going to equal little f evaluated at u times u prime of x. And that's by the chain rule. So in this case, our u of x is 4x minus 2. So our derivative, of course, is just going to be 4. So then f prime of x is going to equal 1 over 4x minus 2. So that's 1 over t evaluated at 4x minus 2 times 4. So we'll get 4 over 4x minus 2 is f prime. For number 2, however, we have 2 variables here. So we have 2 variable expressions. So we'll just note that if we were to evaluate this integral, we would get, let's use a different letter. We would get the antiderivative of 1 over t at x squared minus the antiderivative evaluated at x. And then if we differentiate, we would get 2x g prime of x squared minus x. The derivative of x is just going to be 1, so we just get g prime of x times 1. So you could work it out that way. We could actually integrate this and we would get natural log. So you could try that as well, but really we already can see what this is going to look like. So f prime of x then can simply be written as 2x, and then the derivative of our antiderivative is just going to be 1 over that function value. So 1 over x squared minus 1, the derivative of x, times 1 over x. But when we do that, we can see that we're going to be able to cancel an x in that first term. So we'll end up with 2 over x minus 1 over x, which equals just 1 over x. So again, all of those previous topics that we've looked at from chapter 4, chapter 3, chapter 2, chapter 1 are all going to be blended in with these new functions. So find the average value of the function. So we'll just recall that average value is equal to 1 over b minus a, integral from a to b of f of x dx. So it's the average of the antiderivative values, or just the area under the curve, if we want to think of it that way. So in this example then, we're going to get 1 over, our interval is 0 to 2, so b minus a is just going to be 2 minus 0, integral 0 to 2, and then f of x, so 2x minus tan 0.3x dx. And so this one we can kind of just do directly. You could do a u sub on the tangent if you want to. And note we can integrate these term by term. So the integral of 2x, of course, is this x squared. And then the integral of tangent, so if remember from earlier, the integral of tangent can be written as the natural log of the secant of that function. But we do have this 0.3 that we have to account for. So working backwards, we'll get 1 over 0.3 times the natural log of secant 0.3x. And all of that is going to be evaluated from 0 to 2. So let's go ahead and work that one out. So at 2, we'll get 4 minus, so 1 over 0.3 is 1 divided by 3/10, so that's just going to be 10/3. And then we'll have the natural log of the secant of 0.6. And then we'll subtract at 0. We'll get 0 squared is just 0 minus 10/3. And then the natural log of secant of 0.3 is just going to be secant of 0, which is 1. So we'll get the natural log of 1. But of course, that is just 0. So really, we're just going to end up with this expression on the left. So if we distribute our 1/2 in, we'll get 2 minus 5 over 3 natural log of secant of 0.6. And if you want to approximate, you can put that into a calculator, but that will be our average value. All right, so that is going to end our notes for 5.2. A little bit of review from chapter 4 as well, kind of mixed in there with these new functions. So definitely for the homework, take some time to go through each type of function and working through those examples. And if you have questions, come by the office hours or send me an email. So until I see you next time, though, take care.